Today we're going to be talking about electron configuration, orbital diagrams, and Lewis structures. But first, Bohr models. Bohr showed that electrons travel in shells, and each shell can only hold a specific number of electrons. So shell 1 can hold up to 2 electrons, shell 2 holds 8 electrons, shell 3 can hold 18 electrons, and shell 4 can hold 34 electrons. So to draw Bohr models of an atom, determine the number of protons, neutrons, and electrons. So carbon has 6 protons. 12 minus 6 gives us 6 neutrons, and we have 6 electrons. So write your protons and neutrons in the center, and then place the electrons in the shell. So our first shell can have 2 electrons, and we have 4 left, and those will go in our second shell. So next we have chlorine. Chlorine has an atomic number of 17, so we have 20 neutrons and 17 electrons. And again, write the protons and neutrons in the center, and then start filling the shells. First shell has 2. The next shell can hold up to 8. So we put our 8 electrons in our second shell. Now we have 7 left, so they'll go in our third shell. We place all 17 electrons. Okay, oxygen has an atomic number of 8. We have 8 neutrons and 8 electrons. So put our protons and neutrons in the center, and then start placing the electrons. 2 in the first shell, and the next 6 will go in the second shell. And so when I'm drawing these, remember that the electrons are in pairs, and so I'm drawing them so we can see the pairs. Potassium has 19 protons, 21 neutrons, and 19 electrons. So we put our protons and neutrons in the center and draw our electron pairs around the atom in the right shell. 2 in the first shell, 8 in the next shell, and then we have 9 left for the third shell. Argon has 18 protons, 18 neutrons, and 18 electrons. So we put our protons and neutrons in the middle and draw our electrons around the nucleus in shells. 2 in the first, 8 in the second, and then the extra 8 electrons around in the third shell. So Schrödinger, you probably have heard of that name from the Schrödinger's cat, but he showed that electrons, they travel in areas of probability density, and his model was the quantum mechanical model of the atom. So this showed where the electrons are most likely going to be found. Each of the orbitals, there's S, P, D, and F, they each have a certain shape and a certain number that they can hold. So S orbitals, they only hold 2. P orbitals can hold 6. So this model led to the development of electron configurations. So S orbitals, they hold 1 pair of electrons, or 2 total. They start at 1s, 2s, 3s, and so on. And these are spherical shaped, so they look like a ball. The next orbital, p orbitals, they hold 3 pairs of electrons for a total of 6. These start at 2p, 3p, and 4p, and so on. And this will make more sense when we get to electron configurations. But these are dumbbell shaped, or like a figure 8. So each one of those is one of the orbitals. Next orbital are d orbitals. They hold 5 pairs of electrons for a maximum number of 10. These are 3D, 4D, and 5D, and so on. And this orbital is clover-shaped. So there are 5 different shapes for the d orbital. And the last one are f orbitals. So f orbitals can hold 7 pairs of electrons. They have 14 electrons in there, the maximum number, and these start with 4f and 5f. So f orbitals are very odd shaped. So an electron configuration is like the electron's address, and it tells us exactly what shells the electrons are in. So the s and p orbitals, they're going to correspond to the period number. The d orbitals are 1 less than the period number, and the f block is 2 less than the period number. And as you go down the periodic table and have more and more electrons, the orbitals get more and more complex, and they keep building on top of each other. So you can see how the s and the p orbitals are right with the period number. The d is 1 less, and the f block is 2 less. So to write an electron configuration, you're going to read across the periodic table until you reach the element that you're looking for, and write each of the blocks in order until you reach that element. So oxygen is circled, and we'll read across. We have 1s2, 2s2, and 2p4. So we only write as many electrons as we have in that element. Oxygen has 4 in the p orbital. Copper. So again, we'll read across. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9. Iridium, this is a very long electron configuration. So we start at the top, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, because we'll go down to the F block. Now we'll go back to the D, so 5d10, 6p6, 7s2, and back to the F block, 5f and 7. So lithium, it's element number 3. So we have 1s2, 2s1. So the little superscripts, those are the number of electrons in each orbital. So 1s2 for aluminum, it has 2 electrons in the first orbital. And 2s2, it has 2 electrons. In 2p, it has 6 electrons. And 3s2, and finally 3p1. There's only 1 electron in that last shell. So remember that nonmetals will gain electrons to make a full shell, and metals will lose electrons. So for ions, you're going to add electrons for anions and take electrons from cations. So an oxygen ion, it starts out with 8 electrons. It's an anion, so we add those 2 extra, and we have 10 total. So we have 1s2, 2s2, and 2p6, since it added 2 more electrons. So a fluorine ion, it is 2p7. We have 9 electrons. We add 1 more, since it's a -1. So we have 1s2, 2s2, and 2p6. Aluminum is a +3. That means that it has lost 3 electrons. So 1s2, 2s2, 2p6. And a nitrogen ion. So noble gas configuration makes it a little bit easier to write the electron configurations. So to do this, you're going to write the nearest noble gas in brackets. And then you only have to write what comes after that noble gas. So we can see our noble gas is radon. So we write Rn, and then 7s2, 5f5. So astenine is there in group 7. So the noble gas before it is xenon. So we write Xe in the brackets. We have 6s2, 4f14. There are 14 electrons in that F shell. 5d10 and 6p5. Borium. This is in the D block. And we write the noble gas before it, radon. We have 7s2, 5f, 14, and 6d4, 5. And our last example, radium. It's a group 2 element. So we write the noble gas, Rn, and 7s2. So orbital diagrams. These use arrows to show the spin and the address of an electron. So Aufbau's principle says that each electron occupies the lowest energy orbital available. So this means that you start with the lowest one possible and work up. Or you start at the top of the periodic table and work down either way. So we start with our 1s orbital and fill it before we move to the 2s orbital. Then we fill the 2s before we move to the 2p orbital, and so on. Hund's rule, it says that a single electron with the same spin must occupy each energy orbital before additional electrons can occupy the same orbitals. So this means you would place one electron in each orbital before placing a second one. So like this, not like this. So if we have four electrons in a p orbital, they should look like that first example. The Pauli exclusion principle says that a maximum of 2 electrons can occupy a single orbital, but only if they have opposite spins. And so we would show that by drawing the arrows, showing that they have opposite spins. So we have an up and a down arrow, not 2 up arrows or 2 down arrows. So the ground state is the lowest energy arrangement of the electrons, and this is the most stable. And electrons can become excited and jump to a higher orbital. This is what we saw in lab when we did the flame lab. And then when they are excited, they have to return back to ground state, and to do that, they emit those photons of light. That's why you saw the different colors of light in the flame lab. So different things that can cause an electron to become excited are heat, electricity, and photons of the correct wavelength. So we're going to draw the electron configuration and orbital diagrams for each element. So the first one, lithium, it's 1s2, 2s1. So we show our 3 electrons in our orbital diagram. Chlorine. We have 1s2, 2s2, 2p6, 3s2, 3p5. So we can hold 2 electrons in our first shell, 3 in the p shells, we make sure that we fill 1 electron into each orbital before we add a second one. So remember that ions have either gained or lost electrons. So potassium is in group 1, so it's a +1, which means that it has lost 1 electron. So we have 1s2, 2s2, 2p6, 3s2, and 3p6. We have 1 pair in our s orbitals, 3 in the p orbitals, we drew the up and down arrows to show the different spins on the electrons. So determine which rule is broken. So the first one, all of the electrons are going the same direction. They all have the same spin. So that would be the Pauli exclusion principle. Number 20, that's 2s orbital is not full before we moved on to the 2p orbital. So that would be Aufbau. And the same thing for 21. And 22 would be Hund's rule, since they did not fill each of the orbitals before they added a second one in that 2p orbital. So Lewis dot diagrams. This is our last topic for this video. So our first example is nitrogen. It's in group 5. So remember, the group number tells you the number of valence electrons. We write our symbol and draw the electrons around it, starting at the top and moving counterclockwise until we use all of the electrons. So our next example is radon, and it is in group 8, which means that it has 8 valence electrons. So we draw our symbol. And again, we start at the top and we fill each one of the orbitals and then add in a second electron. So when we use ions, remember that they have gained or lost electrons. So magnesium is going to lose 2 electrons, which means that there are no electrons around it. It has a 2+ charge, and we have to put the charge and put the ion in brackets. So we write chlorine. It's an ion, so it's gained 1 electron. We draw the electrons around it, and again we put it in brackets and write the charge, -1. So don't forget to put the brackets around the ions. So for drawing ionic bonds, we count our valence electrons, and we have 1 for Na and 7 for Cl, so we have a total of 8 valence electrons. And since it is ionic, it's going to give or take those electrons. So we draw Na with its 1 electron. Cl has 7 electrons around it. And then we'll write the ions. So we have Na plus and Cl, which took that extra electron, so it now has a full shell. And it is Cl minus. Next example is Li3P. Lithium has 1 electron, but we have 3 of them. And phosphorus has 5, so we have a total of 8. It's a metal and a nonmetal, so it's an ionic bond. So we draw our phosphorus in the center and the lithiums around it. Each lithium has 1 electron. Phosphorus has 5. And each lithium is going to donate its electron to phosphorus. So for covalent bonds, our first example is PCl3. Phosphorus has 5 electrons, chlorine has 7, but we have 3 chlorines. So we have a total of 26 electrons. This is covalent, so they're going to be shared. So we draw our phosphorus in the center and the chlorines around it. And this time we're going to use lines to show the 2 electrons. So each line represents 2 electrons that are shared between the 2 atoms. Then we fill in with the rest of our electrons around each of our chlorine. We have 2 electrons left, and so there'll be a lone pair on phosphorus. So the next example is CH4. Carbon has 4 valence electrons and hydrogen has 1. So we have a total of 8. It's a covalent bond. So they are shared. So we draw our carbon in the center and draw the 4 H's around it. Then we draw a line between the carbon and each hydrogen. So that shows 2 electrons sharing. So hydrogen only needs 2, so that is a full shell for hydrogen and for carbon. Next example is Cl2. Chlorine has 7 valence electrons, so we have 14 total. So we draw our 2 chlorine. And our bond between them, and then we fill in with the rest of our electrons, and that is 14 electrons. So we have CO2, and carbon has 4, oxygen has 6, and we have a total of 16 electrons. This is a covalent bond. So we draw our carbon in the center and an oxygen on either side. And then our bonds between them. So now we go and fill in with our extra electrons. And that is all 16 electrons that we have, but carbon doesn't have a full shell. So 2 of these pairs of electrons are going to go and create a double bond with carbon so that it also has a full shell. Our very last example is CO3, 2 negative. Carbon has 4 valence electrons, oxygen has 6. And then we have that 2 that it gained from being an ion, so we have 24 total. This is a covalent bond, and it's shared. So we draw our carbon in the center. And put our 3 oxygens around it. We draw a single bond to each one and then fill in with our extra electrons. So this time carbon only has 3 bonds. All of the oxygens are full, but carbon has 3. So we'll take 2 electrons and create a double bond with carbon and that oxygen. But there's more than one way that this Lewis structure could be drawn. So we could also draw it like this, with the double bond between the other oxygens. And so when we have multiple ways that we can draw Lewis structures, this is called resonance.